And this is going to, like I said, it'll work for anything as long as you have no view to the outside world, right? You're in an airplane, and the airplane is not a bumpy ride at all, then in theory you wouldn't know whether you're moving or not. A better example would be a nice, modern, smoothly riding train that's going not only going at constant velocity, but it isn't rocking back and forth at all. Without looking out the window, Galileo says that there's no experiment that you can do that would determine whether you are actually in motion or not. And like I said, it's going to move for any work for any moving vehicle, including planet Earth. I said a moment ago we could do experiments on planet Earth here, and we're stationary. We're not in a moving vehicle. We're in a room that's grounded in a building. But having said that, planet Earth itself is moving at about 18 miles a second around the sun. So we are kind of our own giant moving vehicle, but yet everything is as if we're standing still. So Galileo's point again is that there is no absolute motion. You can take anything and break it down into a frame of reference and determine whether you're moving or not, but it's only relative to something else. If I'm on a train and I'm moving 30 miles an hour and it's smooth, when I'm inside the train it feels like I'm not moving. So I could equally argue that the Earth is moving underneath me and I'm perfectly still, and the people on Earth can argue that no, we're perfectly still and the train is whizzing by us. Galileo says both are equally valid. Consequence of this relative motion, again, we've got the train here, and if I'm moving constant velocity on this train, I could take my tennis ball and I could throw it straight up, and it's going to come straight down from my perspective. Why? Because it's my own free-floating independent reference frame. If I'm going a constant velocity of 45 miles an hour down the track, that means at some point early on, everything from a dead stop was all accelerated to 45 miles an hour, but in unison as a unit. So now once we have achieved 45 miles an hour, that's true for everything. The train, me, everything else inside it, including the ball. So we all now have a velocity relative to the ground of 45 miles an hour. And remember we said earlier that it not only takes energy to speed things up, but it would take energy to slow things down too. And since we're all barreling down the track at 45 miles an hour, when I throw my tennis ball straight up, it's not going to start slowing down on its own and go flying to the back of the train. It's going to keep moving with me, but since I'm moving with it, it looks like a straight path up and down. To somebody on the side, on the embankment, if this were a glass wall and the train was going by on the track and they could actually see through that glass wall there, they would see the path is a little different, because when I throw the ball up and it comes back down, they're going to see it as something like that. Okay? So, quiz question. If a person on a moving train throws a tennis ball 15 miles an hour in the forward direction, and the train is traveling 45 miles an hour, what is the speed the ball is traveling? The answer is, there is no absolute answer. And again, that's the heart and soul of Galileo's relativity. If I'm the one on the train, then to me, the ball is leaving my hand at 15 miles an hour. If I'm the person on the embankment looking through the glass wall, then I would actually add the 15 miles an hour plus the 45 miles an hour from the train, and for all practical purposes, the ball relative to the ground is going 60 miles an hour in the forward direction. The whole point is that both answers are equally valid. There is no absolute answer. It's all relative to who you are and what frame of reference you are in at that time. Okay? So that, in a nutshell, is Galileo's relativity. And so all we need to do now is just kind of go from Galileo's relativity to Einstein. Einstein actually preserved Galileo's relativity and just added to it. And so the big thing that he focused on was incorporating light and the properties of light into Galileo's principle of relativity. And after he did that, it then became what was called the special theory of relativity. So we need to learn a little bit about light first here, okay? A few years later, astronomers Cassini and Romer, they were obsessed with the planet Jupiter and its moons. In particular, I can never pronounce this. Some people call it Io. Probably depends on whether you're a Sting fan or Ed McMahon. But anyway, they pretty much stumbled onto a fascinating discovery about light when they were actually tracking the orbit path. Much like our own moon around the Earth, Jupiter's moons revolve around Jupiter. And the great thing about that sort of thing is it's very, very easy to time this stuff down to the minute, even the second. So we know, like with regard to our own moon and the position of the moon and the sun, we know when a total eclipse is coming. We had one not too long ago. So they can get it timed down to the minute, the location on the planet where you need to be to see this. Same thing with comets. So it's very, very easy once you know the orbital path of anything, whether it's a comet or a planet or a satellite or whatever. You can pretty much predict where it's going to be and when. So these guys are tracking the different positions of this moon, and at some point later, after they thought that they had it tracked, Cassini was looking at Jupiter, and he was saying, well, it's just about time for this moon to re-emerge from the back of the planet out to the front where I can see it again, and at the time it was supposed to come out, it didn't come out. Waited a few more minutes, still didn't come out. Now this is a very curious thing because you know, what happened to the moon? It couldn't have sped up or slowed down or changed its time in its orbit. It's a very, very fixed thing. But yet, and it eventually did reemerge from the back of the planet, but it was several minutes late. And this was just something that bugged him. He turned the information over to Romer. Romer tracked it, basically came to the same conclusion. And what they had determined was there wasn't anything wrong with Jupiter, there wasn't anything wrong with the moon or its orbit schedule or anything like that. It's just that that very last batch of times that they were looking at Jupiter, it was much farther away from Earth than all the previous times that they were tracking the progress of the moon around Jupiter. So what they had concluded was that the light from Jupiter took a lot longer to reach them this time around, and so any event, which is basically light is shining on that event and bouncing it back to their telescopes here on Earth, that light is going to take longer to reach their telescopes. So that's why there was that delay, and they had determined that light actually has a finite speed. It takes time for the light from Jupiter and its moon to get from itself all the way to their telescopes here on Earth, and depending on how close Jupiter is to Earth, will determine how long it takes for that light to happen. So nothing was haywire about the schedule. They had just pretty much made that amazing conclusion about light. And with the different distances of Jupiter, they were actually able to conclude that the speed of the light is 186,000 miles per second, which is pretty accurate. It's pretty close to what they use today. All right, so that's light. We'll get back to that. Got a couple more scientists here, Michael Faraday and James Clerk Maxwell. And they were, like Cassini and Romer were obsessed with astronomy. These guys were obsessed with electricity and magnetism. What's a magnetic field? Well, if you have a bar magnet, we know that magnets have a north and south end to it. If you took a second magnet and tried to connect it to it, depending on which end it was facing, they might connect together with attraction, or if you flip one of the magnets around, they might repel, right? And they can attract to paper clips, iron filings, and that sort of thing. And there's actually a magnetic field emanating around the magnet. With electric fields, they're not quite as commonly discussed in the general public, but you know, when you're talking about charged particles, electrons, protons, that sort of thing, they actually have these electric fields, force-type fields, kind of like magnetic fields emanating from them. Simple example is if you've got a couple socks that are stuck together when you're taking them out of the dryer, you've got some static electricity. There's some communication between some electric field there that's forcefully holding those socks together. Okay. So Faraday and Maxwell, basically, they did experiments and mathematical equations to go along with them. Maxwell took care of most of the math. Established that a changing magnetic field induces an electric field. And Maxwell later provided a conceptual model for changing magnetic field inducing an electric field, as well as changing electric field inducing a magnetic field. So that even though they're two technically different things, they actually have a relationship with one another and affect one another. Okay? This gave rise to a better understanding of electromagnetic radiation, because when one actually induces the other, and then that one induces the first one, and it kind of self-perpetuates, you've kind of got this alternating electric, magnetic, electric, magnetic, electric, magnetic, and it will actually disperse out in wave form. And that's what we've got. We've got electric fields and magnetic fields affecting one another and dispersing out as waves. Maxwell developed equations that allow him to determine the speed of this electromagnetic propagation. Again, we've got, examples where one actually helps generate the other and vice versa, but it's just in an outward wave. Well, these things take time, and Maxwell was actually able to use, through some of his equations, determine how much time this whole process would take. The speed was calculated to be approximately 186,000 miles per second. Well, that's interesting because Maxwell knew that light was 186,000 miles per second. So what are the odds? So he basically correctly determined that light is actually an electromagnetic wave. So in order for us to fully understand Einstein's special relativity and how it adds to Galileo's principle of relativity, we need to understand a little bit about light, and that's actually what light is. It's something that actually has a finite speed, and it is actually, once light is generated, it's dispersed outward as a wave or particle. But we can get into that debate some other time. So it was thought that light must travel through an invisible medium, similar to how sound waves travel. And scientists referred to this medium as the ether. To use the sound wave example, let's say, for example, if I'm, don't try this at home, but if I'm barreling down the thruway on top of a tractor trailer, and I've got two air horns attached to the middle part of the tractor trailer, and one person is at the back of the trailer and the other person is at the front, and the trailer is moving in this direction, and I hit those air horns simultaneously, the person in the front of the trailer is actually moving away from the sound waves that are being generated. The person in the back of the trailer is actually moving toward the sound waves that are being generated. So even though I hit those air horns simultaneously from the center, the person in the back of the trailer will actually hear the sound before the person in the front of the trailer, because one is moving toward, the other one is moving away. That is because sound is generated in the medium that we call air in this particular case, although it could be easily generated in water or any other medium, as long as there's a medium for it to be there. And it's the medium that actually allows these sound waves to propagate and for you to actually hear the words, right? So, in 1886, Albert Michelson and Edward Morley constructed a device that they hope would detect this ether wind. In other words, for sound waves to propagate, their medium was the air. In order for light waves to propagate, their medium was something unknown, but it was assumed to be something, they just didn't know what. It worked by sending light waves in multiple directions and was capable of measuring time difference for each direction. In other words, they constructed a device here on Earth that was basically converting planet Earth into a giant tractor trailer barreling down the road, so that when they activated this device and the light waves actually bouncing in all the different directions, they wanted to see if it had the exact same effect and to what extent as the sound waves generated from the very directional tractor trailer. When the results came in, however, they showed that the travel times for each direction to be equal. So that was completely what they were not expecting. They were actually expecting the results for it to be preferred in one direction or another, just like one person hearing the sound waves sooner than the other person hearing the sound waves, but that's not what happened. So this was very confusing to scientists because they were hoping to establish some sort of medium for these light waves to be traveling in, and they couldn't quite put their finger on this actual medium or this ether that light was supposed to be traveling in. That brings us to Einstein. So Einstein developed the theory, the special theory of relativity in 1905, and by the way, that's what he looked like when he did all his really super important work that we remember him for, although he was a little older when he did general relativity. But most of the pictures of Einstein are that really, really long flowing hair and the mustache, and his first major contribution, or contributions I should say, in 1905, he looked like that, okay? So his special theory of relativity starts out by saying, postulate number one, Galileo's principle of relativity is to be preserved. That is, all motion at constant velocity is to be considered relative, and the laws of physics for moving frames of reference are the same as laws of physics that apply to stationary frames. In other words, everything that we just explained about Galileo a moment ago, Einstein is saying is all true, we're keeping it all, okay? His second postulate, the velocity of light is to be considered constant regardless of the state of motion of the light source. So, why do you think he did that? Well, Einstein thought a lot about Galileo's principle and how light as an electromagnetic wave could play a role in Galileo's principle without actually ruining the principle of relativity. He couldn't imagine a world where you could be locked inside of a boat or a spaceship or a car or anything going constant velocity, in being able to do any kind of experiment where you would be able to determine that you're moving or not. That did not make sense to Einstein at all.